Hello. All right, so now I'd like to introduce Natalie Silvanovich from Google, who has spoken at REcon before on the Tamagotchi thing that she did, which was cool. So welcome back.
Thanks. And I think I have to say up front that this talk has nothing to do with Tamagotchis because people keep asking. So I'm sorry to disappoint you, but today I'm talking about Adobe Flash, specifically finding and exploiting bugs in Adobe Flash. I've been doing a bit of a security review of Flash for over a year now, and I found lots and lots of bugs. So today I'm going to share with you guys some of the highlights, some of the most interesting bugs I've found, and how I exploited them. But before I begin, who am I? I'm Natalie Silvanovich, and I'm a security researcher on Google's Project Zero. Before I was on Project Zero, I worked on mobile security at BlackBerry and on Android. And something that a lot of people don't realize is up to about 5 years ago, back in the dark ages, it was fairly common for mobile devices to use VMs as a root of trust. The most common one was obviously the Java virtual machine. But there was even one BlackBerry device, the BlackBerry Playbook, that used Adobe Air, Adobe Flash, as its main VM. So that's how I really got into Flash. And when I joined Project Zero, that was something I wanted to look at right away. So now I'm a real Flash enthusiast. I love finding bugs in Flash, and I love making the sad puzzle piece appear. And currently, I find 1/3 of Flash vulnerabilities, about 100 bugs so far. So what's my goal? I want to find all of the Flash vulnerabilities. I want to find every last one, and sometime around 2022, I will have found the very last Flash bug, and that'll be it. Flash will be secure. Of course, that's not a realistic goal. What I really want to do is make Flash better. I want to find as many bugs as possible to reduce the bug density so it becomes harder to find bugs. And me and my team, we've also been working on Flash mitigations to make it more difficult to exploit Flash in the case that a bug does get found. So what will I talk about today? To start off, I'm going to do a quick overview of the attack surface of Flash for people that aren't familiar. And then I'm going to talk about how I find Flash bugs and give some sample bugs. And finally, I'll talk about the new mitigations in Flash and how to exploit Flash bugs and give an example of a Flash bug that I exploited. So Flash has 3 main components. The first one is ActionScript 2. This is the legacy Flash VM. It's basically a big interpreted for loop, the very first VM that Flash had just when it was started. It has a reduced API set. It was eventually replaced with a different VM, AS3. So it really only has the features that Flash had early on. And I would say it generally has more bugs with a lower exploitability. It has a lot of bugs because it's so old, a lot of design choices were made that would not be made today. So it becomes a lot more difficult to both prevent new bugs in ActionScript 2 and to fix the existing ones because there's things that a lot of VMs have, like automatic type checking, that just isn't possible based on how this old VM is designed. The flip side is bugs in it tend to have lower exploitability because sometimes when you're exploiting a bug in something, you need to use other stuff, other features of the software to make your exploit work. For example, you need to fill up a slot on the heap and use it for a use after free or use it or overflow it. And with AS2, because the features are limited, sometimes it's a lot harder to find that thing that will make your exploit work. So bugs in AS2 tend to have lower exploitability. And yes, it is true that you can open up a frame in AS3 and load AS2, and sometimes that's enough to get your exploit working. But sometimes it isn't. There's a lot of bugs, and I'll show you some examples of these, where the window is very narrow, and the only thing that you can execute between, say, freeing a pointer and the pointer being used is AS2. So sometimes it can be difficult to exploit these types of bugs, though there are a lot of them. Also, there's kind of blurry boundaries between the VM and the APIs. As I said, this is just a huge for loop. AS3 is the answer to AS2. It's a modern VM with a just-in-time compilation and a fallback interpreter. It's extendable. If you really want to write your own Flash APIs and compile them into AVM3, you absolutely can. It has two heaps, a garbage collected heap, which I would describe as a non-strict, non-exact. It's not very aggressive, but it does eventually free everything. There's also a fixed heap, and this is used for certain fixed data types like bitmaps, where you want to actually manually allocate and free the memory. It's optimized for Flash, but you can use it for whatever you want. In fact, both of these components are open source. AVM3 is open source as Tamarin on Mozilla, and the heap is open source as MMGC on Mozilla, so you definitely can find and build these yourself if you want to. There's open source and closed source APIs. So all the really common core Flash classes like array and vector and that sort of thing, they're open source. And then there's some proprietary APIs, things like bitmap filtering that are proprietary to Adobe. And I'd say in AS3, bugs are less dense but more exploitable. It's harder to find bugs because it's better designed, but if you do find one, you have tons and tons of features you can use for exploitation. And the final part of Flash is what we call the anti-corpus. And this is all the functionality outside of script. So this is the MP4 parser, zlib, regex, image decoders, all the libraries that process data types but aren't really part of script. And I also want to start with a quick warning. Objects in Mirror are larger than they appear. If you've ever tried to exploit Flash, one of the problems you'll come across is the objects are really, really big. In fact, they're way too big for these slides. So for some examples, I've really compressed them. I've made pointers to pointers to pointers, just pointers. And these are conceptually correct for what I'm describing. But if you want to try this at home, it isn't going to work in some situations. So if you want to see the nitty-gritty details of these bugs, I'd recommend you check out the Project Zero tracker. I have all the details there. So how can you find a Flash bug? There's three main ways. You can do it through code review. You can do it through reverse engineering, especially using IDA, or you can do it through fuzzing. And to start off, I find most of my bugs through code review. I'd say the plus side of it is it finds deep, unusual bugs. I'd say at least until this year, when you found a bug through code review, you could be pretty sure that no one else would find the same bug, or it was fairly unlikely, although there's starting to be a lot more contention on Flash bugs these days. Of course, the downside is it requires source, but as I said, a lot of Flash is open source. A lot of ActionScript 3 is. It takes a bit of an upfront investment. It's not easy to code to understand, so it takes a while to figure out what's going on. But once you put in the investment, you can find bugs quite quickly. For example, when I started looking at Flash, once I ramped up, I was finding one bug a day for like several weeks until I started slowing down. So once you understand the Flash source, you can find bugs quite quickly. One of the types of bugs that's really easy to find through code review is type confusion bugs. And fundamentally what these are is casting one type to another type that's incompatible. And one of the best type of type confusion bugs is when you can cast an integer to a pointer or a pointer to an integer, because then you can start messing with memory you're not supposed to modify. These tend to be highly exploitable, though there are a few ones that aren't so good and don't have as much potential. They're the easiest to find through code review or reverse engineering. And they're very common in ActionScript 2, because as I said, they don't have the automatic type checking features that ActionScript has. That said, you can still find type confusion bugs in ActionScript 3, and I'm going to give you an example of an atypical ActionScript 3 bug that involves type confusion I found. And it has to do with how exceptions work in ActionScript. And for VMs, figuring out what to do with exceptions is actually quite hard. I have my grumpy cat here, and he's saying both designs are bad, because there's two ways you can handle exceptions from natives, and both of them have their problems. The way ActionScript 2 does it is if you're running a native code and that native code calls into script and that script throws an exception that's not handled, it will keep going in the native. And the positive of that is you'll never end up in an unexpected state due to an unexpected exception because it keeps running. The downside is that sometimes developers think when they throw an exception it'll stop execution, and it doesn't. And I've never seen a bug in Flash due to that problem, but I have seen bugs in other VMs due to that problem, so it is a bit of a concern. ActionScript 3 behaves differently. It takes the other choice. If you throw an exception from script in a native in ActionScript 3, it'll stop execution. And the problem with that is dangling pointers. If you can throw an exception at any time and it's in native code, then maybe you freed something, then you throw an exception, and then that pointer is dangling. So that can be a problem. Of course, the plus side is that an exception always stops execution, which is sometimes what people expect. So in this case, this is in AS3, and it occurs due to an exception that you can catch, and they fixed it by making it a fatal error. Basically, they threw an exception that should have been fatal, but it isn't. So here's this bug. It both occurs in code and in the Swift file. On the left, I have the code, and on the right, I have the assets in the Swift file. And these are something you can just modify using a hex editor. And you'll notice you can have different assets of different types. I've got a font there and a video there. And then part of the problem here is that there are fixed assets, and these are ones that are created by the VM, and they have reserved values. Unfortunately, you can just overwrite these reserved values, and your self-defined thing will replace them. But that would be okay, except for the exception handling. So in this code, you create a text field, and then this creates what's called a movie object, and it has a pointer to this asset. But then it actually detects that it's the wrong type. And then what it does, which is kind of weird, is it changes the type to the right type. And the reason it does that is so that it doesn't detect this error again, and you don't get stuck in a loop when you're trying to shut down the player. But unfortunately, the player doesn't shut down if you catch this exception. So then you can just create a new text field, and then it will create this pointer again. But now it's of the wrong type, but you've actually corrected it to be the right type. So that's type confusion. You're casting this font type to the text field type. And that's probably an exploitable bug. Another type of bug I saw tons and tons of were what I call superconstructor bugs. And these occur in ActionScript 2, and they have to do with how you can override a constructor in ActionScript 2. I have here an example of the memory layout of an object in ActionScript 2. And this is actually quite relevant in a lot of the bugs I'll show you. In ActionScript 2, all script objects are the same size. So if they're a video or a large image or whatever, that doesn't matter. They have the front script object, which is always the same size, and then they have a backing object, which varies in size and has the real contents of the object, like the video or the image. And what's interesting is they also have a corresponding delete function. And this will free any memory that gets allocated as the part of creating this backing object. For example, let's say it's an image, and then this backing image object has a pointer to more pixels. There's no way to free that meaningfully unless you can also define a function to free it, because you don't know when it's going to lose its last reference and get garbage collected. So that's what they do. You can define this function. And then the last important part of an object is the properties, and this is the proto, and everything you consider to be an ECMAScript property. So if you say, A.B equals C, B equals C will go in your properties table. So how this bug happens is when you call a constructor, this is the flow. First, you fetch proto and constructor, and that just gets the script code that contains the constructor. And then you call the constructor on the object. But if you know how object-oriented programming works, that can't just call the constructor, because you have to call the superconstructor first, and then the superconstructor, and then the constructor. So it goes through this chain and calls the super chain, and then it calls the constructor. And that should set that native data and its corresponding destroy func. But that's optional, because, for example, your backing object could just have integers in it, and those don't need to be freed. And this is actually the problem, and I'll show you why. Here's a bug that I found recently. I think it was fixed in the March update. And it's a bug to do with superconstructors. So the first thing you do is you create a watch on an object. And a watch is something that every time the value of this variable gets changed, it'll trigger some code that you can define. So you set this watch, and then you call the file reference constructor. And what this does is it immediately tries to change this property that you have a watch on. So you jump into the function that you defined, and then you can redefine the constructor like this. And then you can call into the superconstructor. And what that does is, as I said, it sets the native data, and then it sets the destroy func. And then that's done. But you have the previous constructor you tried to call, and that needs to still unwind. So it unwinds, and it sets this bitmap type to the file reference type. But as I said, I'm setting the destroy func as optional, and this object doesn't need to. So you end up having the wrong delete func for a different object, and that's once again type confusion, because it tries to cast something to the wrong type. Another interesting type confusion bug was this one, which I found in October. And what was kind of interesting about it is I reported it, and then 2 weeks later it was found in the wild. It's type confusion in serialization behavior, and it's due to some kind of weird behavior that was implemented in the VM. I also found 2 similar bugs, which were fixed in an emergency patch. And I just want to mention that none of these bugs compile. I'm going to show you conceptually what the code for the bugs does, but you can't really compile this code. You actually have to alter the bytecode in the Swift to make it work. So to start off, this is from the open source AVM code, and this is an interesting check. What this check does is it looks for a binding and checks whether it's binding none. And what this is actually doing is making sure that when you extend an object, you're not overriding a function with anything that's not a function, like an integer. And something you'll notice about this check, which is like a lot of interesting checks, it is commented out. It does not actually perform this check, and that is very problematic. So to make it a little bit clearer what you can do that should violate your sense of all things object-oriented programming is you have up here the superclass, and then you extend it by creating this public var that is an integer that has the same name. And you absolutely should not be able to do that, but you can. So where this gets interesting is for these functions called writeExternal, and then there's a corresponding one called readExternal. And what they do is they're a way to override serialization. So if you're using Flash and you don't like what the serializer is doing, you can define these functions, and then the next time you try to serialize something, it will just give you the object, and your code has to give the byte array back. And then for the corresponding one, it will give you the byte array to deserialize, and then you have to give it the object. So to do this in the VM, what it tries to do is fetch this writeExternal function so it can call it to serialize something. And you can see the first thing it does is it gets this function binding, but it's not a function binding, it's an integer, because you can totally override one with an integer. And then it calls this method binding to method ID, which you can make that so that it steps outside of this array because it's not actually a method. And then you're calling this virtual method on just memory that is somewhere on the heap that you can control. So this was an exploitable issue that turned up in the wild. And you can see how it happened due to that commented out check in the VM. So the next way that a lot of people find bugs is using IDA. I think this is the most common way that people find bugs. This is completely citation needed. This is just based on me asking people who find a lot of bugs how they found them. Like with code review, it finds a lot of deep, unusual bugs, and it has a long ramp up, and it's slower to find bugs, but still, I know a lot of people have been very successful with this method. One of the interesting bugs that came out of reverse engineering was what I call movie clip use after freeze. And these were first found by Bilo, as far as I know, and he found them using IDA. And it's a very, very common class of bugs. More than 100 of them were reported this year, and by this year I mean 2015. And they're still continuing to be reported. Actually, at Pwn to Own this year, 4 out of 5 of the bugs were of this class. They still keep being found. The downside of them is that they have a small variety of free objects. There's lots of these bugs, but they always use after free the same thing. And I think we're starting to get to the end of them being exploitable without other bugs. But they're still there. They're still exploitable in some situations. And the root cause of this bug is actually fairly interesting. It happens because there are certain display fields in Flash that really get freed if you free them, even if there's still references to them, which, is not the way that things are supposed to work, but it was designed this way for an important reason. Basically, in Flash, you can imagine you're trying to make a text field scroll across the screen. And one way you might implement this is create text field, delete text field, create text field, delete text field, create text field, delete text field. Now imagine you had garbage collection instead. It would be create text field, garbage collect, which would cause lag, and then create text field. So for these specific objects, they really delete them, even if there's references, so you don't have that lag situation when the garbage collector runs. But obviously, this is problematic for security reasons. More specifically, this is also an ordering problem. It happens when function parameters are converted after local variables are initialized, but before they are used. And it can be fixed by enforcing a convert initialize use order. And if you look at, for example, browsers that can be susceptible for this type of problem, that's typically what they do. They have a strict coding style that says you have to convert things first, and then that prevents the use after freeze. And it's hard to be sure you're always doing something in the same order in code, but even making an effort to do things in this order can really reduce these bugs. So here's an example of one I found recently. I think this one was fixed in March. It's a use after free due to the add property method. So the first thing that happens is you create a movie clip, and that creates the script object and then the backing object, like I showed in the other example. And then you add a watch to the A property of the function. So I showed that there, and this once again calls into script every time you change that property again. And then you call this function add property. And this function, the first thing it does is it creates pointers to these objects locally on the stack. And then it will try and set this A object as it adds the property, which is a getter or a setter. So it does that, and then this calls remove movie clip, which is one of those functions that really deletes the movie clip. And then you have these dangling pointers that are used in the rest of the function. So the third way you can find bugs in Flash is through fuzzing. And I've done a lot of this with my colleague, Matthias Hurek. And we've fuzzed a few surfaces, basically all three I talked about, AS2, AS3, and Anticorpus. So far, we've just done generation fuzzing, where you mutate a template. Though I do know there are people out there who do generation fuzzing. I've got some bug reports in Flash where the POCs are so insane and have so much code in them that there's no way that they ever would have been produced other than with generation fuzzing. But I've never tried this personally. One thing I noticed about the Flash fuzzing, and this is true about a lot of things, is that it's very dependent on the templates. Like a lot of software, Flash has all these features, and most Swifts use like 30% of the features. So it's important to have a really broad set if you're going to do mutation fuzzing. I find the bugs are lower quality, and that's why I have kind of faster question mark. You do find a lot of bugs, but a lot of them are null pointer exceptions, and you can spend a lot of time going through the bugs trying to find the good ones. But we've definitely found good bugs that way. And the last thing is that heaps really matter here. One of the early problems that we had with fuzzing was that we would have test cases that would actually exercise a bug, but it wouldn't crash. And there's kind of two ways you can get around that. One is if you're building the AVM yourself, you can actually put it in debug mode, and that just puts CA, CA, CA over the heap every time you freeze something. And it's a really crude method, but it does find a lot of use after freeze, because every time you freeze something, it guarantees if something uses it and then treats it as a pointer, it will crash. The other way you can do this, if you don't want to recompile stuff, is just create a Swift with a frame that really churns the heap a lot, and then load stuff in the frame. And then that makes it more likely that stuff will crash if there's a use after free or some other heap bug. So here's an example of another use after free that we found with fuzzing. I thought there were kind of two interesting things about it. One is, I looked for this type of bug, and this was one that I did not find looking for this type of bug, even though I probably should have. And the second thing is that we did find this through fuzzing, and it's an MC use after free. So this shows that at least some of this type of bug can also be found through fuzzing. So this works like the previous NC use after free. You create a movie clip object that has the backing object. And then in this case, you create an object, and then you use the add property function properly now to actually add a getter or a setter. And then you call this vulnerable function, which is duplicate movie clip. And like in the other example, it creates pointers to this, and then it will trigger the getter or the setter when it calls this method, which what the object does is when you create the movie clip, the object is used to set its properties, so it runs through every property and tries to copy it, which is what triggers the getter. And then you can use that to delete the movie clip, and then once again you have this use after free situation. We also found tons of bugs through media fuzzing. We started off doing MP4s and other media types, and we found a few bugs, heap overflow and zlib codec, MP4 file causes stack corruption. And then there was an image fuzz bug I used as the 5th bug in Pwn to Own this year by Tencent. And they used a heap overflow in image processing. So I got back in March and was like, yeah, we totally have to start fuzzing images. And this found, I've got 3 bugs here. A few of them are heap overflows, one of an out-of-bounds read, and I have ... because there's a few more that are going to be fixed this week. And this is actually quite a promising way to find bugs. So now I'm going to talk a bit about Flash mitigations and how to exploit some of these bugs in Flash. And Flash mitigations in the past year, there's been 3 big stages starting last August, starting with the vector mitigations. So the vector mitigations deal with an exploit method that actually has been seen since 2013. And the way this works is there's an object in AS3 in Flash called a vector, and it has inline metadata, a length, and it also has the inline data, which can be integers or objects or any type. So what the attacker would do is they would allocate a vector that would fit in a slot that got corrupted. And what was really nice about these vectors was, they can be big or small, or they can be any type. So you could really get one allocated anywhere you had a bug, and then you'd clobber the length field, and then the next time you access this vector, you could access anywhere in memory space because there was no length check anymore. And the vector mitigation did a few things to get rid of this. To start, it added checksums to vectors that are checked before doing sensitive functions. So now if you do clobber the length of a vector, then when you try to access it, it will fail checksums and then crash. The other thing it did is it put some vectors on their own heap page. And this makes it less likely that a bug that is able to overwrite those vectors will happen in the first place, because they're on their own heap, that there's nothing but vectors on. I would say in general this had a few effects. One is that it definitely reduced the reusability of exploit code. There were lots of situations, including the hacking team dump in August, where we saw that certain people were just using the same exploit code over and over again. And this at least forces them to write some new code for every new bug they use. Also, I would say it generally increases the quality of bug needed for an exploit. Some of the bugs I saw exploited with this method were, really, really low quality bugs. Things like, there is 1 byte at location 27 where 3 bits of it can be set, that sort of thing. And I think this mitigation makes it less likely that the very, very low-end bugs are exploitable. If you have a good bug, it's fairly easy to get around this, but if you have a bad bug, it becomes a lot harder. Some people say that you can substitute the byte array or bitmap data, but this is not as good. What was really good about the vector was that you could change the size of it, and the byte array and the bitmap data are set type, set length. So if you have a bug where you happen to be able to slot one of those in, yes, you can overwrite these, or you could at this point and then get rewrite memory access. But once again, you need a special bug. You can't use any bug for that. The second iteration set was the ISO heap. And what this did is it split the heap into 3 partitions: the pointer partition, the non-pointer partition, and the dangerous partition. Pointer one, it was obviously everything with pointers. Non-pointers is data, and dangerous is things that have a history of being exploited. And of course, this isn't quite perfect because there's some objects that contain both pointers and data, and you have to decide where to put them. But it does make exploitation a bit more difficult, because if you think about it, most exploits involve at some point confusing data for pointers or confusing pointers for data. So if they're all on their own heaps, then that's a lot harder to do. This iteration also put checksums on the byte array, so if you could clobber one, once again, it would fail a checksum check as soon as you tried to access it and then cause a crash. And it also included some JIT spray mitigations, and this prevents a situation where you use JIT to create a lot of code that you can put the instruction pointer anywhere into. There are a few exploits that involve that, and this makes that more difficult. So to give an example of the impact of these mitigations, I'll share with you this bug, which was found in the wild in December, and it wasn't the most interesting bug in itself. It was an integer overflow in the open source verifier. But what was interesting was that the Swift contained 2 exploits. One was pre-August, and it was a typical vector exploit. And then one of them was recent that got around the mitigations. And it included such elements as if statements nested 95 times that are 650 characters long, using both an AVI file and an image to fill heap slots at different points in the exploit, triggering the bug 670 times, and then eventually they corrected the checksums on a byte array, and that's how they got read-write memory access. So there's kind of two things to learn from here. One is that this didn't prevent exploitation, but two, they had to really, really want to do it. You can just see how much work this was compared to the vector exploit. So now there is the third mitigation set. And these were a few changes in heap partitioning, fairly subtle, just changing where certain things went that were prone to exploitation. They also added a bitmap data checksumming. That was another object that tended to get overridden, and also they added extendable checksumming so that if this happens in the future, it's really easy to add checksums to a new object. They've also recently implemented free zeroing, so certain objects, when they get freed, they'll get zeroed right away. And this is sort of a mitigation because it prevents some exploits, but its real benefit is in discoverability. There were some use after freeze where you look at them and you're like, how did that not happen in normal use? And then you look some more and it would be like, well, that actually did totally happen in normal use all the time. And this will make all of those crash and hopefully be more detectable and get fixed more quickly. So I'll share with you an exploit I wrote for a bug I found in February, and it bypasses the ISO heap iteration 1, but not iteration 2, because the bug closed before then, and it requires a separate info leak. So this is a bug that Matthias and I found through fuzzing. And, you know, look at this proof of concept. I bet you guys all can totally see what's wrong here. What was actually wrong here is so in ActionScript 2, which is what this code is in, when you call a function, it allocates on the stack memory, but there's a minimum size, so that'll actually allocate 8 bytes, even though it's 0. And then with this particular function, then you convert the first arg to a string, but there is no first arg, so it calls this uninitialized value on the stack. And first, it checks whether the pointer ends in 6, and it returns if it doesn't, and then it calls a virtual method on it. And that's kind of a weird thing to do. This has to do with how type checking works in Flash. There's situations where the unaligned bits of the pointer are used to check the type of a pointer in Flash. So that's what this check is doing. It's checking whether this is an object type and then using the pointer and converting it. So looking at this, there's kind of 3 ways you can exploit it. To start off, you know, it's definitely exploitable if ALSR is bypassed. If you can do that, then you can obviously call a virtual function on something and get code. But without that, there's a few different options. One was to use an absolute pointer, but in that case, you definitely have to bypass ASLR separately. Another idea was to initialize the pointer as a pointer of the wrong type, right? Maybe you could get a pointer to something else on the stack and then use it. But the problem with that is that ending in 6 thing, right? That really limits the pointers you've got, because how many pointers are there really that end in 6? I had 2 ideas for this. One was that I could use a string and maybe get a string offset that ends in 6 when you're doing some sort of arithmetic. But the problem with that is because the strings are UTF-16 strings, you only get 2 zeros and then it terminates, which means that getting a 64-bit pointer in there would kind of be hard. The other thought I had was to use a bitmap to do that, but it actually has the same problem. Bitmaps in Flash, the subsequent bytes are all multiplied by the first byte due to transparency, so that was also not really an option because you can't get arbitrary values in an image very easily. The third idea I had, which was actually prevented by the ISO heap, was to use a stale pointer. If I could get a pointer to an object, then that would end in 6, and then you could free that object and then get it to point to something else, then maybe you could write an exploit that way. But with the ISO heap, at least in 64-bit, there were only 2 other objects that were allocated in the same slot as the object that was freed, that were the same size as an object that gets freed, the specific type that the pointer that ends in 6 points to. And both of these were kind of useless. They had lots of zeros in them and that sort of thing. So that wasn't really an option. So I ended up using option 1 because I accepted at this point that I had to use a different bug to exploit this original bug. So I paired it with this other bug I found, and this is read-only use after free in the sound class. And it also has to do with exception handling, like I explained earlier. So to start off, you create this sound object. And this sound object, it actually does have the other object pointing to it, but I haven't shown that because it's not relevant in this case. But you have this backing object, and then it points to the MPCM data. So you create this new class, and right now the pointer isn't set to anything, and then you create a byte array, and this one has 1,000 bytes. And then you call this function, and what this does is it allocates memory for this array, and then it loads it out of the byte array that you've allocated, so that memory is there. So then you create a new byte array, and this one is size 2. And you call this function again, and it deletes the array, and then it tries to read out of the byte array, except there isn't even enough data for a float there. It's only 2 bytes, so this throws an exception, which you can then catch. And this pointer is now dangling, and you then use this pointer into memory using the extract function. So this is a fairly good info leak. But the isolated heap actually made this a little bit problematic too, because the PCM data is pointers to data, and ideally you'd like to get a pointer to a pointer so you can read one out and bypass ALSR. So I had to look around quite a bit before I found something that could be allocated in the data partition. I eventually found that when the AVM is calculating JIT, it sometimes allocates a specific object with a vtable on the data heap. So then I could use this bug, make the PCM data just the right size so that this object gets allocated there, and then read out the vtable, and then that bypasses ALSR, and now I know where everything is. So moving on, the next problem here is that I need some contiguous buffers. And this is, I'd say, an ongoing problem in Flash exploitation. There actually aren't a lot of good contiguous buffers in Flash. And as the heap gets more separated, it's getting harder. Most of the contiguous data types, like byte arrays and vectors, are now in the dangerous partition. So I ended up combining these two methods, palette map and determine preferred locales, to create some contiguous data buffers. So starting off, we have determine preferred locales. And this is one of those functions, you just look at the signature and you can tell that it's going to be useful. You have the 2 vectors that are input. And what's kind of cool about these vectors is you can control both their lengths and the lengths of the string, and that's very useful. So you have this character buffer that you can control the length of, or the character star buffer that you can control the length of, and then you have the string you can control the length of. So the first thing you do is you get this allocated somewhere where the sound PCM was, and then you can use the sound bug just to read where that was. And once you read it, this will probably get deallocated, but it doesn't matter. You know what the pointer to that string is now. And then eventually this string will get freed too. So then you need to use this other function. And this is another one where you can see just from the signature that it probably allocates contiguous data because it has all these arrays in it. And actually what it does is it creates them as integer arrays and then copies them into memory. So you set this up so that it gets allocated as in the same spot as this string, which is also data. So now you have this interarray that you can control that's allocated exactly where the string is. So now you have both an array you can control and a pointer to it. And I'll explain what's in the array in a second. And this is good, but you actually want 2 buffers because this specific bug, the original unwatch bug, it calls into a virtual function. So ideally, you'd like to create a fake object with a fake vtable and then call into it. So what you do is, of course, just do this again with a second rectangle and a second call to determine preferred locales, and then you can get the pointer to the memory and a pointer to this red array. And then the final thing you have to do is trigger the unwatch bug. And this is the code I actually used to do it. You can see it's basically a recursive function involving this function called swap depths. And what this does is it makes the stack really, really high. You can't do this generally calling recursively in Flash because the Flash stack isn't the real stack. But if you do a thing where you have a native method that calls into a script method that calls into a native method, and the calls are all from the native methods, you can build the real stack really, really high and then put stuff on it. And in this case, I'm putting a string on it. And little known fact is in Flash, if a string is static and less than 256 bytes, it's actually allocated on the stack. So that was a nice and easy way to get data on the stack. Now, one thing that was problematic about this, I mentioned earlier that strings in Flash are UTF-16, so it's hard to get lots of zeros in them. But funnily enough, that's only the case in strings you create dynamically in script. If you have a string in the SWIF that has different zeros in it, this will actually come out in memory fine. So the way my exploit ended up working was that I created one SWIF, and you load that one SWIF, and that one bypasses ALSR, and then it creates these structures in memory, and then it gives the right pointer to a web app that I just wrote in Python, and this Python generates a new SWIF that has all the pointers in the static strings, and then you load that SWIF, and that'll actually trigger the bug with the correct pointer in it. So this is how it works then. You have the unwatch function. It passes this 6 check because you're giving it a pointer that you calculated yourself. And then it gets converted to the object. You call the virtual function. And then this calls into this array, which acts like a vtable and indexes to where this middle int is. This will call your ROP gadget, which will then call system with the whatever command you put at the top, and that's code execution. So that's pretty much it. In conclusion, finding bugs in Flash is generally getting harder, and I find the kind of relative usefulness of each of the methods is changing over time. As I said, when I started, I was finding 1 bug a day with code review, no problem. Now I'm down to about 1 bug a week, and other methods that are a bit slower, like fuzzing, are starting to become more useful. But it seems to be that there's also trends with these types of techniques. The more you find bugs certain ways, other people will start doing the same thing, and they start getting more depleted. So I suspect over time I'm going to end up using all of these to find bugs, depending on where they're still available. I'd say mitigations are also effective, but it's definitely possible to exploit stuff as well. So I think it's important that we do both of these, both improve mitigations and keep finding bugs so that there's less of them and Flash becomes more secure. So that's it. I want to end off by thanking Adobe. They were actually quite helpful in this research. They've been really good about both fixing my bugs and implementing mitigations. So that's it. I'd like to open up for questions. Question in the back? Okay, thanks. Any more questions? Okay, in the back.
The Flash type system, what can you say about it? I mean, it seems like many of these dangling pointers could have gotten type checked.
Yes, that is true.
So, why not?
There's a few reasons. ActionScript 2 is definitely the worst for type checking, and I think that's just because they, back before there were really a lot of vulnerabilities in Flash, and before, exploits in the wild were even really a thing, even in the 90s. This was when it was designed, and they made this decision where we're going to have an object with a pointer to the object and a type, and the developer has to manually check that every time they make a call, or else it could be an invalid. And that causes tons and tons of problems. And I think if they could do it today, they wouldn't. In ActionScript 3, that's actually a lot better. They made it so that you define stuff as stubs, and then the code that does the type checking is auto-generated, and that's way better. That makes type confusion happen a lot less. The reason it still does in ActionScript 3 is actually usually because a developer didn't follow conventions. They intentionally did something weird that they weren't supposed to, and that caused the problem. So I guess TLDR, I think the AS3 is reasonable, but the mistakes made in AS2, can't go away. There's no way to fix them at this point.
I'm sorry. Can you retrofit some of that to AS2? I mean, you would break some code, but...
Yeah, I think at this point it would probably require writing the whole thing over. It would just be such an extensive change.
Last question. So Blitzableiter, right?
Sorry, what?
Blitzableiter, the Recurity Labs older Flash mitigations. Have you tried looking what those exploits would do against that?
Yeah, I'm not sure. I actually don't know anything about that.
Felix Lindner and his group a while ago did a bit of flash hardening at the time of AS2, I believe. So.
Yeah, I'm sorry, I haven't seen that.
But it's been a while.
Okay. Okay, so that's it.